So the adjoint or Hermitian conjugate, sometimes called adjoint. Physicists use the name Hermitian conjugate, which is more appropriate, or, well, I don't know if it's more appropriate. It's more pictorial if you have a complex vector space. And you're accustomed in linear algebra about Hermitian matrices, what they are, and that will show up a little later, although with a very curious twist. So given an operator T belonging to the set of linear operators in a vector space, you can define T dagger also belonging to L of V. So this is the aim, constructing an operator called the Hermitian conjugate. Now, the way we're going to do it is going to be defining something that is a T star. Well, I said T star because mathematicians, in fact, call it star. And most mathematicians, the complex conjugate of a number is not Z star, but Z bar. So that's why I call it T star. And I may make this mistake a few times today. We're going to use dagger. And so I will make a definition that will tell you what T dagger is supposed to be, acting on things, but it will not be obvious, at least at first sight, that it's a linear operator. So let's see how does this go. So here is the claim. Consider the following thing. U, T, V. This inner product of U with TV. And think of it as a linear functional. Well, it's certainly a linear functional of V. It's a linear functional because if you put A times V, the A goes out, and if you put V1 plus V2, you get it's linear. So it's linear, but it's not the usual ones that we've been building in which the linear functional looks like U with V. I just put an operator there. So by this theorem, there must be some vector that this can be represented as this, acting with that vector inside here. Because any linear operator is some vector acting on the vector V. Any linear functional, I'm sorry, not linear operator. Any linear functional, this is a linear functional, and every linear functional can be written as some vector acting on V. So there must be a vector here. Now, this vector surely will depend on what U is. So we'll give it a name, and we'll call it, it's a vector that depends on U, so it's a vector that depends on U. I'll write it as T dagger U, where at this moment, T dagger is just a map from V to V. We said that this thing that we must put here depends on U, and it must be a vector. So it's something that takes U and produces another vector called T dagger on U, but we don't know what T dagger is, and we don't even know that it's linear. So at this moment, it's just a map, and it's a definition. This defines what T dagger U is, because some vector, it could be calculated exactly the same way we calculated the other ones. So let's try to see why it is linear. So claim T dagger belongs to the linear operators on V. So how do we do that? Well, we can say the following. Consider U1 plus U2 acting on TV. Well, by definition, this would be the T dagger of U1 plus U2, some function on U1 plus U2, because whatever is here gets acted by T dagger times V. On the other hand, this thing is equal to U1 TV plus U2 TV, which is equal to T dagger U1 V plus T dagger U2 V, and by linearity here you get equal to T dagger U1 plus T dagger on U2. And then comparing these two, and this is true for arbitrary V, you find that T dagger acting on this sum of vectors is the same as this thing. And similarly, how about AU TV? Well, this is equal to T dagger on AU V. Now, T dagger on AU, do you think the A goes out as A or as A bar? Sorry? A or A bar? What do you think T dagger on AU is supposed to be? A, because it's supposed to be a linear operator. So no dagger here. You see, well, I didn't show it here. Any linear operator T on AV is supposed to be AT of V. And we're saying T dagger is also a linear operator in the vector space. So this should be with an A. We'll see what we get. Well, the A can go out here, and it becomes A bar, well, no, I'm sorry, A star, U1 TV, which is equal, I'm going through the left side, by definition, A bar, T dagger of U, V, and now the constant can go in, and it goes back as A, T dagger U, V. So this must be equal to that, and you get what we're claiming here, which is T dagger on AU is equal to A T dagger of U. So the operator is linear. So we've defined something this way, and it's linear, and it's doing all the right things. Now, you really feel probably at this stage this is still not all that intuitive. What does this all do? So we're going to do an example, and we're going to do one more property. And let me do one more property and then stop for a second. So here is one property. ST dagger is supposed to be T dagger S dagger. So how do you get that? Not hard. U STV. Well, STV is really the same as S acting on TV. Now, the first S can be brought to the other side by the definition that you can bring something to the other side putting a dagger. So the S is brought there, and you get S dagger on U, T on V. And then the T can be brought here and act on this one, and you get T dagger, S dagger, U, V. So this thing is the dagger of this thing, and that's the statement here. There's yet one more simple property that the dagger of S dagger is S. You take dagger twice, and you're back to the same operator. Nothing has changed. So how do you do that? Take, for example, this. Take U, put S dagger here, and put V. Now, by definition, this is equal to, you put the operator on the other side adding a dagger, so that's why we put that one. Like this. The operator gets dagger, so now you got the double dagger. So at this moment, however, you have to do something to simplify this. The easiest thing to do is probably the following, to just flip these two, which you can do, the order by putting a star. So this is equal, the left-hand side is equal to this. And now this S dagger can be moved here and becomes an S. So this is V, U, U, S, V, and you still have the star. And now reverse this by eliminating the star, so you have S, I'm sorry. I have this notation completely wrong. SV, this is U. The U's and V's are easily confused, so this is V, and this is U. I move the S, and then finally I have SU, V without a star. I moved it, flipped it again. So then you compare these two, and you get the desired result.